Welcome back. Let us continue with the semiconductor devices and applications. In the previous video, we have studied PN junction diode, VI characteristics of PN junction diode, diode parameters, effect of temperature on diode parameters, wherein we have studied about with the change in temperature, the parameters like forward current, forward voltage are going to vary. And next we have studied about the DC approximation characteristics, wherein we studied three approximate characteristic model of the PN junction. So in this video, we are going to study about the DC equivalent circuit of semiconductor diode, how to construct a DC equivalent circuit, and why do we need with DC equivalent circuit. Then the DC load line analysis. So what is the DC load line analysis and why do we go with using DC load line analysis, and to determine some of the parameters using the DC load line analysis. Next, AC equivalent circuit and the Zener diode in brief with its VI characteristics and some parameters that are essential for your further consideration of the topics. Let's the DC equivalent circuit of a semiconductor. So, an equivalent circuit for a device is a circuit that represents the device behavior. That means a device behavior means how the circuit is going to respond to the application of the DC voltage. So, this equivalent circuit is the simplified representation of a complex circuit. It retains all of the electrical characteristics of that complex circuit, and this coequivalent circuit is essential to determine the impedance of any of the complex circuit. So for an example, if you say if you are having a circuit with more than one resistor or impedances, you can say, so this can be transformed into a equivalent circuit consisting of one resistor with the voltages if any applied. So this is the equivalent circuit for this set of resistor. So in the same way for a diode, so when you say a diode, we already know the characteristics of a diode. So when you consider a diode in any of its state, or if you consider a diode, it is going to have one resistance for the flow of current and it can be represented with a voltage source. So this is one of the model representation of a diode already we have considered earlier. So likewise, this DC equivalent circuit, when you say with the application of DC voltage to the diode, how it is going to respond to that particular diode. So a DC equivalent circuit may be substituted in place of the device when investigating a circuit containing the device. This says that whenever we are having a complex circuit consisting of diode, apart from the diode, you may have many of the other components. With those components, when you apply a voltage source to those components along with this diode, so this diode DC model. So let's see what are the different DC models for the diodes. So for an ideal diode, when you say when the forward biased, a constant forward voltage Vf is assumed with negligible forward resistance. So when we assume the diode to be ideal, we say that the diode is nothing but a voltage source. So we represent a diode with a single voltage source Vf, and this Vf is the forward voltage essential for the flow of current when forward bias. In this case, the DC equivalent circuit is assumed to be a voltage cell. So this is a voltage cell with a voltage of Vf as shown here. So an ideal diode, already we know about an ideal diode, it is going to have zero resistance. Resistance is equal to 0, and there is a current I flowing through the circuit at a voltage Vf, and this is the voltage that appear across the diode over here. So thus the diode is replaced by a voltage cell VF. So this is for an ideal diode. And now next we can consider accurate equivalent circuit of a diode. So when you say an accurate equivalent of a diode, you can go with all these characteristics. When a diode is forward biased at a voltage V equal to 0, there exists a resistance R for which the current I is equal to 0. So and this resistance is due to the depletion region. So already we have studied with this. So now once we overcome with this depletion voltage, that means with the increase in voltage V equal to Vf, then there is a resistance, then also there is a flow of current IF, and this resistance is the dynamic resistance RD, dynamic resistance RD. So for this circuit, for this accurate diode, we are going to represent it with its equivalent circuit having the contents or the characteristics, one with the voltage Vf and the other one is the resistance RD. So that is represented using this figure. So where the resistance RD will be in series with a voltage cell with a voltage of Vf. This will be the accurate equivalent circuit for a diode, and this is also called as a piecewise linear equivalent circuit. So while studying in the piecewise linear approximation of the characteristics, we have seen that we have considered one diode model which is having a dynamic resistance RD. So in that case, we see that from the voltage 0 to Vf, the current flowing through the diode circuit will be 0. So after a voltage Vf, there is a that is approximated by the linear line with a slope equal to Rd. The slope is equal to Rd, which is the dynamic resistance. So this circuit is also called as the piecewise linear equivalent circuit of a diode. These equivalent circuit are essential to determine the current flow in the diode circuit with the applications of some voltage sources, wherein with one resistor and a voltage source, it is easy to apply with the Ohm's law. So now let's see the determination of the current prevailing in any of the diode circuit. So with this is to do this or to determine this, we use the DC load line analysis. Next, we will study about the DC load line analysis. So DC load line analysis is the graphical analysis of a given diode circuit. So when you consider a diode circuit with a voltage supply E, resistance R1 in series with the diode D1. So after a forward voltage at Vf, there will be a current flow in the circuit that will be equal to If. So in order to determine the current and voltage parameters, we go with using this DC load line analysis. So when you apply the Ohm's law to this to this diode circuit, E is equal to If R1 plus Vf will be the Ohm's equation. Sorry, Ohm's law, that will be the equation for this circuit. So using this circuit, you can determine the parameter If if the voltage E, R1 and Vf is known. In the same way, you can determine the resistance R1 if E, If and Vf are known, and so on. So when we use this equation, there will be the approximately the value of If and Vf can be determined. So to find the precise value of the current in the circuit we go with this graphical analysis called the DC load line analysis. Okay, in this DC load line analysis, we will draw a DC load line on the forward characteristics of the diode. Forward characteristics. Already we have studied with the forward characteristics over in the previous slides. So a load line will be drawn on the forward characteristics curve. So let us see how to draw the DC load line on the forward characteristics curve. This DC load line is a straight line. So this is a straight line that gives all the DC conditions that exist within the circuit. DC condition means for a particular voltage V, there exists a current I. So all the values of current I for a particular voltage in this straight line, that will be the DC load line. So to understand this DC load line, we need to have 2 points. When you say a straight line, so if we have to draw a straight line, you need 2 points to draw a line. So we have to determine those 2 points that are to be plotted on the forward characteristic curve. So once you get these 2 points, you can draw a DC load line. So to determine these points, we will go with this further equations. So for this diode circuit, if we apply the Ohm's law, it is E equal to IF R1 plus VF, and this equation we will consider this as the load line equation for our further evaluation. For any circuit, for this circuit, E R1 is the series voltage and D1 is the diode, E is the applied voltage. So with this, we will go with the determination of 2 points A and B on the forward characteristics curve to draw a DC load line. So here this is the forward characteristics curve that we can consider for a diode, and the plot of DC load line on the forward characteristics needs 2 point A and point B. So knowing 2 of the points, we can draw a straight line that will be the DC load line. So to determine the point A, in order to determine the point A, here we assume that IF is equal to 0. So assuming IF is equal to 0 for that circuit and applying that into E is equal to IF R1 plus VF. The equation here with IF will become 0 is like this, where VF is equal to E, right? So in this case, VF will be equal to E. Then the point on the x-axis, that is point A here, is E comma 0. Okay. Then to determine the point B, we assume VF as 0. Point B is on the y-axis, so the x component VF is assumed to be 0. So applying this VF is equal to 0 into the equation, IF R1 plus VF goes like this. So now when VF is equal to 0, this term will be 0, and E is equal to IF R1. This implies that IF is equal to E by R1, right? So that point B is 0 comma E by R1. Now this will be the point B on the y-axis with 0 comma E by R1. So by joining point A to point B, we'll get the DC load line. And this DC load line is going to intersect on the point Q and called the quiescent point. This is the intersection of the forward characteristics curve and the DC load line. So this is how we are going to draw the DC load line by determining the point A and B with the parameter assuming IF is equal to 0 for point A and VF is equal to 0 for point B, and then joining the point results with the DC load line. Next, we'll consider the quiescent point, or the quiescent point, also called as the DC bias point. So in the previous slide, we have seen that when we draw a DC load line on the forward characteristics curve, so with the point A and point B, here we see that there is the intersection of line with the forward characteristics point, and this is called the Q point. Okay. So and also we have seen that the slope of this DC load line will be equal to the resistance R1 that we have connected in series with the circuit. So the circuit in the previous page, we have seen a voltage source E in series with the resistor R1 and a diode in the forward biased condition. So here with this will be the circuit what we have considered earlier with a voltage Vf here. And we have seen the determination of the point A and point B. So point A is E comma 0 and point B is 0 comma If by R1. So knowing these 2 points, when we draw a DC load line, this intersection point is the Q point. And this is the point on the DC load line where the diode voltage and current are compatible with the circuit condition. The voltage and current at the quiescent point gives the precise value of the circuit. When you say the precise value of the circuit for a particular voltage resistors R1 with voltage drop Vf, the forward current If can be considered. This will be the precise value of the current voltages at the point Q. Quiescent point in turn gives the precise value of the circuit present in that particular condition. So next, let's consider calculating the load resistance. So in the previous slide, as we have seen, the draw of DC load line. So using this DC load line, we can determine the parameters of the diode. So knowing the value of E, I, we can determine R1, E and I, you can determine Vf. Like that, some of the parameters can be determined. So now with the DC load line, let's see how to calculate the load resistance R1. Okay. In the diode circuit, resistor R1 dictates the slope of the DC load line and supply voltage E determines the point A on the DC load line. This says that the point A can be determined by knowing the voltage value or the supply voltage E, and the slope will be giving the DC load line slope gives us the resistor or the load resistor R1. So the circuit condition can be altered by changing R1 or E. So if you change the value of R1 or V, there will be the change in the circuit. So example, we have seen that for the Ohm's law, from the Ohm's law, we have written the equation E is equal to If R1 plus Vf. Okay. So by varying the value of E, there will be a variation in If, or by varying R1, there will be a variation in If and E. So but this Vf will always be a constant for any of the diode depending on the type of the diode. So by varying R1, If varies. If E is varied, If varies. So like that. So now let's see how to determine the load resistance using the load line analysis. So for that, if we start here, for a diode circuit given the forward current and supply voltage, when you want to determine the forward resistance, you will be given with the forward current If and the supply voltage Vf. So this is very much essential for your examples, numerical examples. So next, the load resistance R1 can be determined, okay, by using these following steps. So these are essential for your numerical analysis. First, to determine these values, so knowing If and E, the load resistance is calculated by the slope of a load line. Okay. So to do that, first you have to draw the DC load line. Given with these parameters, you have to draw the DC load line. And the equation for the circuit, earlier we have seen it, E is equal to IF R1 plus VF. So as you considering this equation, now let's see the point A. The point A is plotted at IF is equal to 0 and VF is equal to 0. So while drawing the DC load line, we have seen that to determine the point A, we assume IF is equal to 0. In that case, with IF is equal to 0, we see that VF is equal to E. So you will get the first point E comma 0 on the x-axis. Okay. So next, to determine the point B, the IF, whatever you are going to have, the current IF are R1. We know that it is IF, the forward current, by R1 comma 0. So earlier we have seen that for point B, it is 0 comma IF by R1. So in this case, R1 is unknown. So we have to determine the value of the R1. So, but the value of IF is given. You cannot determine the point B now. Okay. Then we'll move to the next point on the DC load line. The next point at the DC load line is the Q point. So B cannot be determined as the resistor R1 is unknown. Now we'll see another point Q. To draw a DC load line, you need at least any two of the points. So B is not there. Now let's check with Q point. So the Q point is plotted on the forward curve with a specified IF. So IF is given. So knowing the value of IF, you can plot it on the forward characteristics curve. So here we will be having the list of value of the IS. So whatever the given value is there, for that particular point, we will draw a line so that it will be being towards the forward characteristics curve over here. So that point is our Q sign point, where the value of IF is specified. So knowing this Q point, now we can join A to Q. Further, if we produce this load line towards the y-axis, it is going to intersect somewhere on the y-axis, and that point will be our, so where you can have the value for IF and R1 can be determined. Then the load resistance is the reciprocal of the slope of the DC load line. We have seen that the R1 is the slope, right? So that means R1 can be determined by using delta VF and delta IF. So these are the incremental value. So knowing this DC value, this will be the incremental value of VF, and this is the incremental value of the IF. Totally we are going to consider it and find the slope, that will be the resistor R1. Okay. Once again, when we go with first, point A is plotted using IF is equal to 0 and VF is equal to voltage E. So you will get with the point over here. Then the point B is unknown. So one more point is the Q sign point. It is plotted by using the given value of current IF. So we will produce a line towards the forward characteristics curve. Wherever it is intersect is the Q point. Then drawing a line from A to Q and producing further it to B gives us the complete DC load line, the point B. Then the slope of this DC load line will be determined like this. Delta VF by delta IF gives the load resistance R1 or the series resistance R1. Okay, is it clear? So next go with the next topic. Then to parameter, the calculate supply voltage using the load line. Determination of the supply voltage. So if the supply voltage is not given, by knowing the load resistance R1 and the current in the circuit, we can determine the supply voltage. So once again the same equation. E is equal to IF R1 plus VF. So VF will always be known. If we know with the current IF and R1, we can determine the so voltage supply E. So once again we go with using the DC load line analysis to find the precise value. First, both the point A and point B cannot be plotted as the supply voltage is unknown. So we don't know what will be the value of E. So the point A and B cannot be plotted. So point A, as you know, it is VF comma 0, and point B is 0 comma IF by R1. So we don't know the value of E and the current, right? So now only the Q point can be plotted at a specified IF. So IF is given, only Q point can be plotted. So considering the precise value of IF and drawing a line towards or projecting it towards the forward characteristics curve, that curve point on the forward characteristics curve, we are having the Q point. Okay. Now, but R1 is the reciprocal of the slope of the DC load line. R1 is delta VF by delta IF. This is known and same as the IF value. Okay. Therefore, delta VF is equal to R1 into delta IF is determined. Knowing the value of R1, delta IF, we will consider delta IF to be the total current 0 to IF itself. Okay, that gives us the incremental value of delta VF, right? From the diode equation, E is equal to IF R1 plus VF, that is known to us. So then E is equal to VF plus delta VF. This gives the supply voltage of the current. By determining the value of supply voltage, point A and the load line can be plotted at VF is equal to E IF 0, and the DC load line can be drawn in turn. Okay. So this is how we are going to determine the voltage or the supply voltage. Supply voltage E is delta VF plus delta EF plus, E is VF plus delta VF. Okay. So knowing the analysis, DC node line analysis, now let's see the AC equivalent circuit of a diode. So the AC equivalent of the diode shows that, or say, will be the equivalent circuit with the application of some AC voltages, or you can say the change in voltage. So as you have seen earlier, with the application of voltage E, we have seen that the DC load line analysis. So when you say AC load line analysis, here we are going to apply either a change in voltage like this, or a pulse, you can say, a period over which it will be positive and suddenly there is a change into the negative supply. So if we say this is applied to the diode, it will be forward biased and suddenly it will be reverse bias. So when we go with this condition, or also application of AC and AC voltage, even this can be considered. So any one we can consider. So now we will study it with a pulse voltage, applied pulse voltage to the biasing circuits. Okay. So when you do with this, we are going to characterize the diode with the capacitive impedance. So let's see how we are going to consider this to be a capacitive. The property or the way it is going to behave will be in the form of a capacitor's property. Fine. So let's see this. When you see the junction capacitance, so when you are going to consider a diode, there exists a junction between P type and N type. So this junction, it behaves like a capacitor. Now let's see how it is going to behave. The depletion region of a PN junction is a layer of depleted charge carriers situated between the two blocks of a low resistance material. So here when you consider this, here you are going to have a depletion region, and these two parts will be the N type and this will be the P type. So this region is depleted of the charge carriers. Fine. So Because this is the description of a capacitor, the depletion region clearly as a capacitance. So by this property, we can say that the depletion region is a capacitance. This capacitance occurs only during the reverse bias condition. So this we'll see next how it is going to happen. The depletion layer capacitance is calculated from the equation of a parallel plate, as you know the equation for that, and typically the junction capacitance is 4 picofarad for a low current diode. So you can once again, when you see here, the depletion region of a PN junction is a layer depleted of charge carriers situated between two blocks of low resistance. This is the property of a capacitor. Okay, so the junction capacitance is going to exist represented by this equation. So a diode represented as a junction capacitor due to the depletion region. Okay, next. A forward bias junction, when suddenly reverse biased, the forward current IF ceases immediately, leaving some majority charge carriers in the depletion region, which has to flow back out of the depletion region. So this means when you consider the diode here, we have a depletion region. This will be the diode depletion region. This is the junction. So there will be p-type, n-type. So in p-type we will be having negative ions. N-type we are going to have the positive ions. So when forward biased, there will be a flow of electrons from n-type to p-type, resulting in the current I. When you apply a pulse, when you see to this, if this is the applied voltage, this will be forward biased. When there is a sudden change in the voltage to the reverse bias. So whenever it is reversed bias, suddenly there will be the ceasing of the current I, or the current I will be stopped. But we see that there may be some electron that have entered into the depletion region. So it takes some time to reduce the current in that case. Suddenly there will be no, suddenly the current will not be equal to 0. When there is a sudden change at this point, I will not be equal to 0. But I will reduce to 0 slowly with the time, okay, due to this parameter. So here this will be the property of a capacitor. When you say a capacitor, when once the capacitor is charged, so at some instant there will be a current I. So when it is fully charged, when we remove the voltage across this, okay, this is how we are going to charge a capacitor. When you remove the voltage, when the voltage is suddenly equal to 0, the current will not be immediately 0. So this current goes down slowly, or the capacitor will discharge slowly so that the current will be 0. Okay. So this property is depicted by a capacitor for a diode. Okay. The reverse current. Next, one more capacitor exists in the diode. So that property shows the diode. This is the diffusion. So firstly it is the junction capacitor CPN, and now we'll see there is one more diffusion capacitor. The reverse current flows, which is larger initially and slowly decreases to the level of reverse saturation current. So this, when we have changed this voltage from forward bias to reverse bias, we see that there is the decrease from some current to 0. So this is once again the capacitive property, and it is depicted by the diffusion capacitance CD for a diode. Okay, this is in the reverse biased condition. For a reverse biased state, we are having the diffusion capacitance. In the forward state, we are having junction capacitance. It is can be shown that CD is proportional to the current IF. So this is the property of a capacitor, already we know with that. So there exists two capacitive property for the diode, and with that capacitive property now we can write the equivalent circuit for the diode. First, when you consider at the reverse bias, so during the reverse biasing, a reverse bias diode can be simply represented by the reverse saturation reverse resistance in parallel with the depletion layer capacitance. So when you are going to reverse bias a diode, there exists a reverse resistance RR, that will be the resistance for the flow of reverse saturation current, and that in parallel with the junction capacitance gives us the reverse biased diode AC equivalent. Okay. Then next, when you go to the AC equivalent semiconductor of a diode for forward biased diode, there exists a dynamic resistance RD. So when you know that for a forward biased junction, you are going to have a dynamic resistance RD, that will be the opposition for the flow of forward current in series with the voltage cell VF. So this will be the equivalent circuit. With that, there will be a parallel diffusion capacitance CD, the equivalent circuit for a diode whenever it is forward biased. Okay. The equivalent circuit for a forward bias diode may be modified to form an AC equivalent circuit for a diode by removing a voltage representing VF from the complete equivalent circuit. This applies to the diodes that are maintained in forward biased condition while subjected to a small variation in IF and VF. So even we can write this as RD in parallel with the diffusion capacitance. Okay. So this diffusion capacitance is due to the reverse biasing sudden. See, one of the important parameter, reverse recovery time for the AC equivalent circuit, right? So before moving to that, let's see here. So when already we have seen that the application of AC is not only the application of a sinusoidal AC value, even you can have a voltage pulse applied to the diode, and here we see that, so this will be the pulse which will cause the forward biasing of pulse is going to cause the reverse bias. Okay. So with the application of the pulse over this certain part of the voltage, the diode will be forward biased and there will be a flow of current IF, right? So now suddenly there is a fall of voltage from forward to the reverse voltage. So when you say there is the fall of voltage, at this point the diode will be reverse biased. When the diode is reversed biased, we always know that the reverse resistance will be approximately equal to 0, or there is some current called the reverse saturation current. In this case, when we go with the pulse, there will be the current reducing from the current IF to some value. Okay. So there will be no sudden fall from IF to 0. There will be the slow reduction from the current IF to RF. So that can be plotted over here. So this graph shows this. When the diode is forward bias, there is a current IF. So now with the fall of forward current, fall of voltage from forward to reverse, we see that at some point the current will be equal to IF only. So from there it starts reducing. So this is because some of the electrons will be moved into the depletion region already. So they have to settle on, that takes the current from IF to the saturation. So when the pulse switches from positive to negative, the reverse current initially equal to the forward biased current IF and then gradually decreases to 0. This is what the property of the capacitor. So slow discharge of current is the property of the capacitor. So that is represented in the AC equivalent. So now the time taken for this action is called as the reverse recovery time. The reverse recovery time is the time required for the current to decrease to the reverse saturation current level. So when the pulse is changed from forward to reverse, the time taken for the current to reduce to the reverse saturation is called as the reverse recovery time. This is very much essential when we have to keep the biasing properly, or to obtain a proper biasing. This will be of importance. So this has to be studied here. Hence, we can say once again, the reverse recovery time is the time required for the current to decrease to the reverse saturation level from IF to the reverse saturation level IR. That is the time taken. And typically the values of reverse recovery time for a switching diodes ranges from 4 nanoseconds to 50 nanoseconds. This once again depends on the type of the doping, or the quantity of the doping that we are going to do in a junction diode. And one more parameter that is essential to maintain the proper biasing is the fault time. This fault time is the time taken for the voltage to drop from forward voltage. This will be the forward voltage to the reverse voltage, right? So this time should be considered here to have the proper biasing that is present here. To keep the reverse current of the diode to a minimum, to make it minimum, the fault time of the applied voltage pulse must be much larger than the diode reverse recovery time. So to maintain this, the minimum fault time, whichever is essential, is equal to 10 times the reverse recovery time. So if this is 10 times the reverse recovery time, then only the minimum value of IR will be obtained. To have this proper value of IR, this is what has to be maintained, that fault time of the voltage from VF to VR. This has to be maintained equal to 10 times the reverse recovery time, the time taken for the current IF to reduce to IR. Okay. So with this, now we'll move with one more diode, special diode called the Zener diode, which is very much essential for your further applications. Let us study about the Zener diode. Before starting that, we already know about the PN junction diode. A normal PN junction diode will allow the current flow in only forward biased condition. So when you are considering a normal PN junction diode, this will be the normal PN junction diode. Whenever it is forward biased, there is a current flow in the diode in only one direction, and there will be a large amount of majority current and a small amount of the minority current. So hence a forward bias junction diode will be offering only a smaller resistance. So for forward bias condition, there will be a less resistance for the flow of current, right? So then whenever the diode is reverse biased, so when you consider a reverse bias circuit, that will be in the opposite direction, the voltage applied will be in this condition. So here the applied voltage will be adding up to the depletion voltage, and there will be a very small amount of reverse current, and the resistance offered will be very high. Okay, so in the reverse bias, already we know that when you see to the characteristics, when we are going to have this characteristics curve, or with the application of reverse voltage, we see that there will be a small current flowing, and after some point, even if you increase the voltage, reverse voltage beyond some value, there will be a breakdown of junction. So this breakdown is due to the avalanche or Zener effect that is going to take place in the PN junction diode. Okay, so if we increase the voltage beyond VR, we see that there will be a sudden rise in the current and there will be a large amount of power dissipation. So due to this power dissipation, the diode will break down and the destroying of the diode takes place, right? If this current is limited, so if you are going to limit this reverse current by a suitable series resistor, the power dissipation can be kept to a level that will not destroy the device. So by using this concept, we are going to design a special diode called a Zener diode, which is going to operate in this reverse region. The Zener diode is a special type of device that is designed to operate in the breakdown region. So if you are going to use a series resistor, you can limit the current flow. That limitations of the current flow will be operating in the breakdown region. Okay, diodes designed to operate in this reverse breakdown region will be having a more applications in the further topics. They are going to, the breakdown voltage remains extremely variable over a wide range of current levels. This says that the breakdown voltage VR can be maintained constant by maintaining a limited value of reverse breakdown current. Okay, so this is a Zener diode. This is designed to be operated in the reverse breakdown region. So in the reverse breakdown region, there are two types of breakdown that will be affected the current flow. There are two types of breakdown, junction breakdown. One is the Zener breakdown. So when the depletion region is very narrow, the electric field strength produced by the reverse biased voltage is very high. This high intensity field causes electrons to break away from their atoms, thus resulting in the conduction. This is ionization by electric field, also called Zener breakdown, and usually occurs with the reverse bias voltages less than 5 volts. So when we are going to use a voltage of 5 volts, less than 5 volts, there will be the breakdown. This says that the Zener breakdown is due to the breakaway of the electrons from their atoms. So when you increase the reverse bias voltage, the electrons will get the energy to break away from their atoms and become free electrons and resulting in the current conduction, right? And the other one is the avalanche breakdown. When the depletion region is too wide, so here the depletion region is wide when compared to the Zener breakdown over there. The electrons in the reverse saturation current can be given sufficient energy to cause other electrons to break free when they strike atoms within the depletion region. So this happens inside the depletion region. This breakdown takes place in the depletion region. So as the width of the depletion region is large, there will be large number of depleted charge carriers. So those depleted ions will get energy so that there will be the release of electrons or breakaway of the electrons inside the depletion region. The electrons thus released will collide with the other atoms to produce more free electrons, and this is called the avalanche effect. This ionization is by collision. This ionization is by collision, and this breakdown will be produced by the voltages above 5 volts. So in brief, we can say Zener breakdown will be appearing in the diodes with very narrow depletion region, and the electrons in the N type and the P type, there they are going to break away from the atom. in the avalanche breakdown, there will be the larger depletion region and the breakdown of electrons will happen in the depletion region. Okay, so these are the two types of junction breakdown that appears during the reverse bias condition. The representation of the Zener diode. So a figure shows the circuit diagram for a Zener diode. So in normal diodes we are having the representation as this form, where this will be the P type and this will be the N type. P type is the anode and the N type will be the cathode according to the previous symbol representation. It is similar. Zener diode is similar to the PN junction diode. So it is also having a single junction having one P type and one N type. So your P type is again represented in the form of a triangle as usual. P type is the anode and the N type, instead of using a bar, it is similarly written as a Z, so alphabet Z, approximately alphabet Z, and that will be the cathode. And usually this Zener diode will be operated only in the reverse bias. So this external voltage supply can be mentioned like this, with P type connected to the negative terminal and the N type connected to the positive terminal. And this again shows the unidirectional or the conventional current direction in the forward biasing state. So in the forward bias, as usual, in the PN junction, it is the conventional current direction. So here it remains the same. But this operation of the Zener diode is always done in the reverse bias with a current of IZ that will be considered in the next topic for the parameters of the characteristic of the Zener diode and some of the parameters that we come across in the Zener diode. So when you say the characteristics of a Zener diode, it can be we usually operate this Zener diode in reverse bias condition. So we are going to consider only the characteristics of reverse biased condition. So when you say the reverse bias condition, the applied voltage will be VR if you consider voltage VR, and the current flowing is considered as IR or IZ here. Fine. So it is considered as IZ. Zener current IZ is considered over here, and VZ, V is the voltage over the Y x-axis, right? So whenever it is operated in the reverse breakdown region, we see that for a certain voltage or till some voltage, the Zener current is very small or negligible. Okay, so it is similar to the PN junction. So after a certain voltage called the breakdown voltage, so in normal we can say this is the breakdown voltage. So at the breakdown voltage, there will be the junction breakdown resulting in a large amount of current. Okay, so the point at which the voltage at which there occurs the Zener breakdown is called the VZ. Okay, VZ is the reverse breakdown voltage. So we'll see this parameter along with this characteristics. VZ is the reverse breakdown voltage. Okay, so after that there will be a sudden increase in the Zener current, right? So the minimum value, so here IZK, whatever the mentioned over value here is IZK, the parameter, it is the reverse current near the knee of the characteristic. So it is near to the knee. It will be the minimum reverse current to sustain the breakdown. So this current is essential to maintain the diode in the reverse bias condition. Below this current, it is still in the reverse biased condition, but after this current IZK, this minimum value of current, it is entering into the breakdown region. Okay, and then till where we can maintain the current. So we have already seen by maintaining the current using a resistor, we can maintain this voltage constant. Seeing to this curve also, we can say over some constant value it is seen over this. Over the some value, the current voltage is constant, right? And that is this voltage current. So IZM. So this is the maximum Zener current that is essential to maintain or to limit the constant voltage Vz. So above this current Iz, there will be the breakdown of the Zener diode. So to maintain a constant voltage Vz, we have to maintain the current between Izk, which is the minimum value of Zener current, to Izm, which is the maximum value of the Zener current. So these are some of the parameters. So like that we can say in this region, whenever we are going to say with a constant, when we have to maintain the current, there should be a resistance. So the slope of this reverse bias region will give the Zener dynamic impedance ZZ. So this ZZ is the dynamic impedance which will be considered to be the from the slope of the Zener breakdown curve. That is delta Vz by delta Iz. Okay, and the power dissipated during this particular region or at the reverse breakdown is power dissipation. Maximum power dissipation is Vz into Iz max. So this is the maximum power dissipation. So by this, maintaining the power dissipation in this level, you can maintain the breakdown region, right? With the current limitations, we can have the breakdown of the Zener diode with the constant voltage Vz and a power dissipation of Vz into Izm, and there exists an impedance delta Vz by delta Iz in the circuit for the flow of current. So this will be the characteristics and some important parameters which are essential for our numerical calculations. So now let's see the Zener diode equivalent circuit. So similar to our PN junction, normal PN junction, we can write the DC equivalent circuit. You already know what is the equivalent circuit and why we go with equivalent circuit and what is a DC equivalent circuit. So with the application of DC voltage, so we know that it is always taken in the reverse breakdown region only. So when we see here the Zener is reverse bias. So if we assume it to be an idle, if we maintain the current between Izm and Izk, we are going to have a voltage of Vz to be constant. So we are replacing the Zener diode by a voltage cell of voltage Vz in the breakdown region, right? So when you apply when you go with an equivalent circuit, there may be a little change in the, or there may be a change from forward bias to reverse or reverse bias to forward bias with a small AC value. If you are going to have, then there exists a dynamic resistance in series with the voltage Vz. So the dynamic resistance ZZ in series with Vz. So these circuit is used in the case where Zener current is varied by a small amount between Izm and Izk. Both the equivalent circuit is used only when the Zener diode is maintained in the reverse breakdown region, right? So these are the equivalent circuit of the reverse breakdown. Apart from that, some with the change in temperature, the parameter like power dissipation and Zener voltage are going to vary, right? When you say the maximum power dissipation, we know that with the equation PD is equal to Vz, the Zener breakdown voltage, into Izm, the maximum Zener current. So the variation of the temperature is going to vary the parameter. So if the temperature T is increased, so if we say the temperature is going to be increased, there will be a reduction in the power by a factor called the derating factor. So this is similar to our PN junction, normal PN junction, right? So here we are having one equation to determine the power dissipation changes at different temperature. So at temperature to determine PD at some temperature T2, we go with using this equation. The power dissipation P2 at temperature T2 is equal to P1 at temperature T1 minus of delta T into derating factor. So this is similar to the PN junction. So here we see that by knowing the power dissipation at some temperature T1, so you can determine the power at some temperature T2 by using the derating factor and delta T. So here delta T, when you say, it is T2 minus T1, that is change in temperature, and this derating factor will be specified by the manufacturer. So by knowing these two parameters, we can determine the power dissipated at some temperature T2. And in turn we can say, with rise in temperature, there is the reduction in the power dissipation. Okay. And one more parameter is the Zener voltage. The Zener voltage at any temperature can be determined by using this equation, right? So the equation Vz2 means at temperature T2 can be determined by knowing Vz1 at temperature T1 plus delta T into alpha Z into Vz divided by 100. So this is the equation to determine the Zener voltage at some temperature. So here we see that as the temperature is increased, there is an increase in Vz also. Okay. And here delta T is again the change in temperature T2 minus T1, and alpha Z is the reverse temperature coefficient. So, and of Vz in per degree centigrade, right? So this is per degree centigrade and specified by the manufacturer. By using this equation, you can determine the Zener voltage at any temperature. So this will be the brief explanation for Zener diode. Hope we have understood the concept. So in this video, we have studied with the Zener diode with its some of the parameters, briefly about the Zener diode, and DC analysis of the PN junction diode, which is essential to solve the numerical problem DC equivalent and AC equivalent circuit. So in the next video, let's study about the application of the PN junction, that is the rectifiers, in the next video. Thank you. Hope you have understood the concept.